Welcome back everyone. In this lecture we will continue with the applications of character theory. So, let us first recall what we have proved so far, and I will set up some notations as well. So, let G be a finite group so we denote this chi 1 etc chi s to be the irreducible characters of G. So, what we do, we choose unity representation from each isomorphism class corresponding to these irreducible characters. So, we denote them by V 1 etc V s. So, here S we want to determine that is exactly the number of irreducible characters of G. So, these are the corresponding irreducible representation, the corresponding irreducible representations of G. So, since each isomorphism class will contain an unitary representation. So, we simply assume that these are indeed unitary irreducible representations of G. So, this is the complete set of inequivalent irreducible representations of G. So, now using complete reducibility, we notice that any given finite dimensional representation. So, any given finite dimensional representation of V, we can write it as direct sum of these irreducible copies. So, in particularly we write it as V 1 direct sum M 1 direct sum etc direct sum V s direct sum M s. So, here each V I occur with multiplicity M I. So, this M I is nothing but the multiplicity of V I in capital V. So, this is what we will be using hereafter. So, now you can actually see that sometimes I want to use this chi rho to denote the character. So, in particularly the rho I, let us say the corresponding representation that corresponds to the representation space V I. So, this is our given representation, let us say. So, we simply identifying chi rho I with chi I. So, this is what I am doing for I range from 1 to S. So, now we already seen that how to determine this multiplicity in terms of the characters. So, if we take this rho to be the given representation. So, this is the given representation. So, then the chi rho is going to be the character of this representation. Then we have seen using this orthogonality relations of these irreducible characters that the computing this inner product chi rho chi I gives us exactly M I. So, this is actually a simple verification. So, let me just quickly do it here. So, we know that chi rho is exactly equal to M 1 chi 1 plus etc plus M s chi s. So, in particularly if we take chi rho chi I for some fixed I, then you can see that this is going to be exactly equal to summation M j chi rho chi I, where I range from chi rho. So, I have fixed chi rho. So, this is exactly chi j chi I where j runs over from 1 to s. So, in particularly using this orthogonality relations. So, this is exactly going to be equal to delta I j. So, then from this you can see that chi rho comma chi I, this inner product is exactly m I. So, this is what we get for the multiplicity in terms of the characters. So, now as I promised, I am going to actually quickly tell you how to actually prove this orthogonality relations using the language of representation theory. So, what are we going to do? Like we will just realize whatever objects that were playing important role in order to prove the orthogonality relations, they are all can be realized as representations of G. So, that is how we can actually kind of rephrase everything in terms of the representation theory language and remember the proof quickly. So, remember that we constructed this projection map, that is from the home space to the G invariant maps, that home G V comma W. So, that projection map indeed played important role. So, here you can see that this home space itself can be realized as representation of G. So, let us say V comma phi is given representation and then W comma rho. So, these are two given representations of G. So, now recall that the home space is nothing but all possible linear maps from V to W. So, this is those maps from V to W which are nothing but C linear maps. So, this is a vector space. So, this is a vector space over C and the dimension of this space is indeed the product of the dimension. So, this is exactly equal to the dimension of V times dimension of W. So, this product formula already suggests that there should be some close relationship between the home space and the tensor product. So, since I have not defined tensor products, so I am not going to use that language right now. So, later part of the course we will actually recall the construction of the tensor product and then I will tell you like how these objects can be realized in terms of the tensor products. But for time being let us just work with this home space. So, what we want to do, my claim is this home space can be realized as representation of G. So, now we want to define the action of G on this home space. So, let us define. So, for that let us take G to be an element in G and F is being an element of this home space. So, in particularly F is linear map. So, now we want to associate from this data G comma F. So, we want to associate some G dot F that is supposed to be element of again our home space. So, how do we do this? Let us define this very explicitly. So, recall that this given G we have this rho G and phi G. So, let me draw this diagram. So, from V to W we have this map F and from V to V we have this map phi G and then W to W we have the map rho G. So, now what we are interested in again defining this G dot F from this V to W. So, from this diagram it is clear that so what should be the map. So, basically we take this phi G inverse and then take compose with F and then again compose with this rho G. So, that is going to define a map for us. So, that is the map that we are going to take it as G dot F. So, G dot F is going to be composition of rho G with F and phi of G inverse. Note that phi G inverse is same as phi of G inverse. So, this is the map that we are interested in. In particularly for any V in V, you define G dot F of V to be just rho G composition F composition phi of G inverse applied on V. So, now we want to verify that this indeed gives us action of G on this home space. So, that means if we take this representation, okay, let me call it pi phi comma rho. So, which is a map from G to this home space, where the image is given as follows. So, G goes to let us say pi G, and which is a map from again home space to home space, which is given by where you take F and then send it to this G dot F, which is given by rho G F phi G inverse. So, this is the representation that we are talking about. So, first thing to prove that this is indeed a representation of G. So, this is a map from G to GL of this. Okay. So, for that we need to verify that the identity map is mapped to the identity homomorphism, identity linear map, and then the composition goes to the composition. So, it is easy to see that pi identity is going to be just identity. So, pi identity is just identity on the home space. So, that is something quickly one can verify, because both rho identity and phi identity, they are identity maps. So, since phi of E is identity and then G of rho of E is also identity. So, that would imply that pi E of F is exactly F. Okay. What's about the second? So, we need to actually verify that the composition of two maps is indeed gives us the composition of pi G1 and pi G2. So, to verify this, we need to verify it on all elements of the home space. So, let us compute what happens to pi G1 pi G2 of F. So, this is by definition rho G1 G2 F phi of G1 G2 inverse. So, now since both rho and phi are group homomorphisms, we can rewrite this as follows. So, where pi G1 G2 of F is going to be exactly rho G1 rho G2 F phi of G2 inverse phi of G1 inverse. So, since this term is going to be equal to G2 inverse G1 inverse. So, when we apply phi, so then using group homomorphism, it will be product of phi of G2 inverse and phi of G1 inverse. So, now you can see that this can be grouped as follows. So, first you apply this pi G2, then you apply pi G1. So, basically this quantity you can see that which is pi G2 of F, and then you have rho G1 times the pi G2 of F and then phi G1 inverse. So, that means this is exactly equal to pi G1 applied on pi G2 of F. So, that means pi G1 G2 is exactly equal to pi G1 composition pi G2. So, this is what one needs to verify in order to prove that this is indeed group homomorphism. Okay, so we verified it is group homomorphism. So, all other things will be taken care because the group has inverses. So, the images are invertible. So, pi g inverse is going to be inverse of pi g. So, that is all immediate. So, that means this home space can be made into representation. So, the home C V W is indeed representation of G, and let us call this representation curly V. So, now we want to understand what will be the fixed point subspace of this curly V. So, recall the definition of this fixed point subspace, you collect those elements from home V comma W such that it is fixed by the action of G for all elements G and G. So, now let us try to understand what happens if we pick some element T from this V G. So, then if and only if T is in V G, then it is clear that G dot T is equal to T for all G, but recall G dot F is nothing but rho of G F phi of G inverse. So, that means we have rho of G T phi of G inverse is exactly equal to T, and this is true for all G in G. So, that means if and only if you can see that rho G of T, rho G composition T is exactly equal to T composition phi G, and this is true for all G in G. So, that means T is indeed intertwining operator, that means T is G invariant map. So, this verifies that the fixed point subspace is indeed equal to the space of G invariant maps from V to W. So, as I said before, so that is how like we were motivated to define the projection P from this big space which is the home space to its fixed point space, where the projection is defined by using this average technique. So, if we have a let us say representation V, so this is the representation, then recall that. So, we can define this projection map from V to V G by taking V goes to this average sum G dot V, where G in G. So, one can divide by mod G so that it becomes identity on V G, and we verified that this projection is indeed defines onto map on V G, and when you restrict to V G it is indeed identity map. So, then we use this projection to do some computation. So, that is the projection that we are talking about here, because if you recall the definition of T hashtag, so which is by definition 1 divided by the cardinality of G summation rho G T phi G inverse, where G runs over in G. So, this is just the average sum of the action of G on T. So, that is how the projection becomes natural, and recall that what we proved, indeed we proved that the rank of this projection is same as the trace of the projection, and whenever V and W are irreducible, then we could use Schur's lemma to compute this trace. But anyway, just once we define this projection, then it is immediate that the rank is same as trace, and then that is exactly equal to the dimension of the fixed point subspace, which is exactly the dimension of home G V comma W. So, this is what we wanted to actually compute. We wanted to compute this, and we realized using this trace identification that this is going to be exactly the inner product between chi v and chi w. So, you can see that once you put it in this language, so all needed was realizing that home space is G module, and then this fixed point subspace captures the G invariant maps from V to W, and we were interested in understanding what happens to this, and that is indeed given by directly by Schur's lemma. So, now this P indeed captures everything about the orthogonality. So, for example, like when we looked at this P and then with respect to the standard basis, we saw that the entry of this P captures the inner product between the matrix coefficients phi I j and rho k l. So, let me recall the inner product between this phi I j and rho k l was given by the entry I j comma k l entry of this projection map, and this trace was just nothing but inner product between the characters. So, that is how like everything about the orthogonality immediately followed from understanding only this projection map. So, indeed in the light of this projection map we could see that orthogonality relations are nothing but immediate consequence of Schur's lemma, but this is something one may not be able to see using just naked eyes, but in a way you can say that basically orthogonality relations are direct corollaries of Schur's lemma. So, but Schur's lemma you can see that it is somewhat very simpler statement to prove, but these orthogonality relations seems like somewhat involved results, but doing all this background work one can see that this just follows from Schur's lemma. Okay, so still we need to, like as I promised, we need to prove that these irreducible characters they form a basis for this space of class functions. So, let us actually try to prove the theorem. So, here is the theorem. So, the irreducible characters chi 1 etc. chi s they form orthonormal basis, orthonormal basis of this space of class functions. Again we fix V G to be finite group. Like I said, this is the complete set of characters chi 1 etc. chi s. This is the set of irreducible characters of G. So, we already proved that it is actually indeed orthonormal set. So, the important thing to prove is that they span this Z of C G. So, there are two ways actually to prove this result. Okay. The first proof which I am going to again give is that in order to prove these irreducible characters actually span this entire space of class functions. So, we prove that the orthogonal complement of span of these irreducible characters, that is going to be 0. So, let us take V to be the span of this chi 1 etc. chi s, and this is going to be a subspace of this the space of class functions. Since this space of class functions indeed a subspace of this C valued functions from the group G, and this is an inner product space. So, from this inner product we can conclude that the space of class function, that is also an inner product space. So, in particularly we have nice inner product to work with. So, like I said, whenever we are working with the inner product, so we are in actually very good situation. So, we can start using lots of linear algebra techniques. So, in particularly if you have a subspace, then you can pick up a unique subspace which is complement to V, which is given by the orthogonal complement. So, to prove V is exactly equal to the space of class functions, it is enough to prove that V perpendicular is 0 inside your space of class function. So, this is how like the first proof actually goes. So, we simply prove that the orthogonal complement is indeed 0. But in the second proof, so what we do, so we directly prove actually this V is exactly equal to the space of class functions. So, by proving that we have already have a very nice basis for this CG itself. So, recall, so these matrix coefficients of all these irreducible characters, so they are going to be orthogonal subset of this CG. So, from them we actually constructed this d1 square plus etcetera ds square number of this orthogonal subset of CG. So, which is given by, so these matrix coefficients, normalized matrix coefficients, where this k runs over 1 to s and then this ij they run over from 1 to di. So, recall that di is nothing but the degree of this irreducible representation rho k. So, I am using like instead of rho k, I am just using this rho power k, because so this ij I need to index. So, but it is understood that what I am using. So, let me go back to my notations. So, you can see that we denoted the representations by rho I. So, we also use rho I same as rho power I. Okay. Sometimes we need to write down the matrix coefficients. For them we just use this ij. Okay. So, the degree of these representations are nothing but dk. So, then if you take the matrix coefficients of this irreducible representation rho k, then you can see that these elements form orthogonal subset of CG. So, once you normalize, then you get orthonormal subset of CG. So, the second proof indeed literally tells us first that this is indeed a orthonormal basis of CG. So, we prove that this is indeed a orthonormal basis of CG. From that we conclude that the span of irreducible characters will be just the space of class functions. So, all these proofs actually requires a step by step process. Okay. So, both proofs actually are somewhat involved and both actually kind of equivalent only. So, they do not really use some different ideas, but it is better to understand both proofs, that actually gives some new insight to the topic. So, both proof actually uses the construction of regular representations. So, maybe I will do that in the next class and then we understand the character of regular representations. Then using that understanding. So, we actually immediately conclude that so these matrix coefficient, normalized matrix coefficients, they form a basis for this CG. So, from that, so we will be able to conclude immediately that the irreducible characters will form a basis for this space of class functions. And almost this statement is also proved using the again regular representations. But anyway, so let us actually stop here and then I will do this proof in the next class. Thank you.